integration. What's that, I hear you ask, because this new foreign word that we've never heard of before. Wow, let's see. I'm going to start with trying to solve a problem. How do we find the area under curve? Now, if the curve was a straight line, not an issue, because we've got formulas for triangles, squares, and we could, cut it up into those shapes and find the area. But when we've got a curve, in this case, it's y equals x cubed, how do we find the area under that? Well, what we can do is estimate. Now, those red rectangles, which we call the outer rectangles, because they go around the outside of the actual area that I'm looking for. Now, clearly, it's too big. But I could find the area of those two rectangles. 1 times 1 cubed plus 1 times 2 cubed. And I know the area under the curve would be less than that. So I know it's less than or equal to 9. Theoretically 9. I mean, there's no way it's equal to 9, but theoretically it could be. The blue ones, which we call the inner rectangles, because they're inside the actual area we're trying to find. Again, I could find those areas, although the first rectangle there actually is just a straight line. And I know the area I'm looking for would be bigger than that. And so we know the area is somewhere between 1 and 9. And I guess logic says, well, if I want to work out an estimate, let's average those values out and we'll have an estimate for the area. So 5 units squared. Turns out that actual area is 4 units squared. How do you know that, I hear you ask? Yes, it's the magic of maths, but you'll see soon. It'll be a mystery until then. So that gave us an estimate. How can I improve the estimate?
More rectangles.
It's a great idea though. Let's do more rectangles. So now I've done 5 rectangles. And so the width now is 0.4 and the heights would be 0.4 cubed, 0.8 cubed and so on. So I now know it's less than 5.76. But again, I could do the inner rectangles. Oh, here, there they are. And I can now trap it between 2.56 and 5.76. The estimate now would be 4.16. So just by going from 2 rectangles to 5 rectangles, I've got a lot better. Remember, the exact area was 4. Well, if 5 improved it, just imagine what 10 would do. Let's do 10. Okay, come on, where are your rectangles? Hey, there we go. Of course, the width of those is 0.2, and then it's times 0.2 cubed, 0.4 cubed, etc., etc., etc. 4.84. The inner rectangles. Keep expanding out. Here they go. And I've now trapped it between 3.24 and 4.84. The average of those two, oh, we're going good. 4.04. Remember, the exact value is 4. So with 10 rectangles, I'm almost there. What would be the ideal number of rectangles?
Infinite.
Yeah. If I could do an infinite number of rectangles, I'd get an exact area. Let's investigate that idea. I've just moved to some random curve, y equals function x. But what we've just seen is, as the width of those rectangles decrease, our estimate is getting more and more accurate. So we're going to just look at one of those rectangles. So let's have a look at it. Now, yes, it looks like the top of that rectangle is curved. Don't be fooled by that. Because remember, if we're trying to make the width as small as possible, then that little curve really is the same as a straight line. I just can't draw it that small, because if I did, you wouldn't see it. And it's kind of important you see the shape. So let's just pretend that is the curve we're estimating is to be. Now, I'm going to invent this new function called the area function. If I can come up with a function for area, then we can find the area, because I just substitute into the area function. Let's call it creatively capital A for area, in case you're wondering why I thought of A. So capital A, that function is going to represent the area from 0 to C, up until the rectangle starts. So area X will be 0 to X, so the area of the rectangle will be the difference between the two. Okay. So area X minus area C will be the area between the two. Let's now actually give it a flat top. So there's the rectangle. Its height would be whatever function x is. Its width is x minus c. So the area that we're looking for is equal to x minus c times function x. Rearranging that, I could say function x is area x minus area c over x minus c. But hey, watch this. Instead of calling it x, I'm going to call it c plus h. H being the width of the rectangle. It's starting to look familiar. Area c plus h minus area c over h. We're saying we want h, that width, to be as small as it possibly can. So we get an infinite number of rectangles. So we'd like h to approach a value of 0. So as h approaches 0, that area is going to become exact. So function x will be the limit as h approaches 0 of this area function, sub in c plus h, minus sub in c all over h. Yes. But hey, if h is approaching 0, c and x is the same thing. So I'm just going to use x instead of c. Just to highlight, hey, look what we've got. It might now start looking a bit more familiar. What is it? It's the derivative. That was our first principles formula for the derivative. So in fact, function x, the equation of the curve, which I know, is the derivative of this area function that I'm looking for. Well, so now we can come up with a way of finding an area under a curve. So if I want to find a curve under any function I like, going between a and b, the area will be what we call the integral. That's a new word. Integral. Yeah. And this symbol here is, it's an S. It's an elongated S. So when they first started doing the calculus in the book, it was actually an S they drew, an elongated S. And over the years it's become the integral symbol. Okay? So originally it was like an S, for exactly what someone said, sum. We're summing up all those rectangles. We're going from A to B, and function x is what we want to integrate. How do we integrate? We've seen this before. The answer is going to be capital F when we sub in B minus capital F when we sub in A. What is capital F? That's what before we called the primitive function. It's the same thing. Add 1 to the power over the power. So let's go back to our cubic. We were trying to find the area under the curve. How did he know it was 4 exactly? X cubed between x equals 0 and x equals 2. Now I can say, well, I know that the area is equal to 0 to 2 of x cubed dx, add 1 to the power over the power, a quarter x to the power 4, substitute in 2, substitute in 0, 4. A note about notation. Okay. Some people think that the smallest number has to always be on the bottom and the largest number has to always be on the top. It doesn't. If I had them the other way around, what would happen? Yeah, I'd just get negative 4 instead of positive 4. So to find area, we do tend to go from left to right. So what is logical? We'll learn some rules a bit later when we'll change that. When I integrate, I then put the new function in, well, I put them in square brackets. And again, we put our limits now on the right-hand side there. And then we substitute those numbers in. The top number minus the bottom number. That is an integral. X cubed, anyone know what that's called? Integrand. That's an integrand. A quarter x4, do you know what that's called? Teach you the good things at tutoring, do they? The primitive function. Ah, there you go. That's a primitive function. Okay, so let's do some others. So I want to now integrate x squared plus 1. Beautiful thing is we just do each piece. We saw that with primitive function. each piece individually. So a third x cubed plus x, and in this case I'm going from 2 to 3. Substitute in. Be careful with your grouping signs, because when you're subtracting it's very easy to lose negatives times negatives, and so remember it's minus all of when I substitute in. And 22 and 3. Notice here I said units squared, the second one I didn't. And there's a reason for that.
Area.
Right. The first one I'm actually using it to find an area. It's a specific problem, so it's units squared. The second one is not, it's just a calculation of a number. X to the negative 3. Negative indices, doesn't matter. Add 1 to the power over the power, so negative 2. Mere mortals. When I substitute in, I tend to get rid of it, because I just think it's easier to substitute without the negative indices and get the number. So it's 1 over 5 squared minus 1/4 squared. All right, let's play.